So we need to find the characteristic equation, eigenvalues, eigenspace, determinant, and trace of the following matrix. Let's do the easy stuff first. So the trace of this matrix is going to be 1 plus 1, which is equal to 2. And the determinant of this matrix, since this is upper triangular, is just going to be 1 times 1 times 0. Oh, that's interesting. So I suppose that means that we're probably going to get, can we get lambda equals 0 as a eigenvalue? Can we get that as an eigenvalue? Yeah, so that means that a bunch of stuff is going to get mapped to the 0 vector. Okay, interesting. Oh, I see. So anything that looks like this, probably gets mapped to the 0 vector, right? So anything that lies on the z-axis. Yeah. I see that. Okay, so 0 is definitely going to be an eigenvalue, but how do we find those things? Let's take a minus lambda I. So a minus lambda I is 1 minus lambda, 0, 0, 0, 1 minus lambda, 2, 0, 0, negative lambda. So if that's the case, this should be, we need to find the determinant of this and set it equal to 0. So the determinant of this particular matrix, since it is upper triangular, is going to be 1 minus lambda, and negative lambda. And we only get non-trivial solutions when our determinant is equal to 0. So that is going to lead us to two distinct eigenvalues. We're going to have an eigenvalue of 0 and an eigenvalue of 1 that has multiplicity of 2. And that makes sense because I know we've talked about this before. The trace of our initial matrix should be the sum of our eigenvalues, including the multiplicities. So 1 plus 1 plus 0. And the determinant should be the product of our eigenvalues, 1 times 0. So it does include the multiplicity. So everything looks good so far. By eigenspace, do you mean the eigenvector? So maybe I said something incorrectly, but yeah, the idea here is that the eigenspace should be the span of our eigenvectors. That's usually what we mean by the eigenspace. So the eigenvectors are a basis for the eigenspace. Yeah, the span of each of your spaces. Yeah. Okay, so if we take a look at what's going on when lambda is equal to 0, what do we get here? So when lambda is equal to 0, we should get the matrix 1, 0, 0, 0, 1, 2, and 0, 0, 0. So we basically just get A back, right? When lambda is equal to 0. This is already in reduced row echelon form. So we should be able to read off solutions directly from each of the rows here. So the first row says that x is equal to 0. The second row says that y plus 2z is equal to 0. And the third row, because we don't have a leading coefficient for z, implies that we're going to have to parameterize our z variable. So here z is going to be equal to t, and if y is equal to 2z, then that means, if y plus 2z is 0, that means y is equal to negative 2z. And factoring out t should give us the vector, the eigenvector that we need that's going to actually span that eigenspace. So something interesting is happening with our vectors that look like 0, negative 2, and t. All of these vectors actually end up getting sent to the 0 vector. Cool. Is that true? Really? So if I take A and I right side multiply by the vector, that looks like this. Does that get sent to the 0 vector? So 1 plus 0 plus 0. 0, negative 2t plus 2t, and then 0 plus cool. So it's actually a little bit of a bigger space than I originally thought. But yeah, all of these vectors should get sent to the 0 vector. That's what lambda equals 0 means. Reese is having a dream right now. Okay, so our eigenspace for lambda equals 0 is the span of the singular vector 0, negative 2, and 1. So the next thing we need to do is figure out what's going on for lambda is equal to 1. We go back and just take a look at our a minus lambda I case. So we should get 0, 0, 0, 0, 0, 2, and 0, 0, negative 1. So 0, 0, 0, 0, 0, 2, 0, 0, negative 1. And if we do elementary row operations, we should get a reduced row echelon form that looks like this. So what does that mean for our vectors that we're kind of interested in? It means that here, so x, y, so this means z is equal to 0. And then I don't really get any other information about what's going on with x and y. So this means that x and y can be free parameters. So we get something that looks like this. We can maybe set x is equal to s, y is equal to t, and then we're going to force z to be equal to 0. And if we factor out the s and the t, we're going to get like s 1, 0, 0 and t 0, 1, 0. The sum of these two kind of vector combinations, the sum of this linear combination should be x, y, z, according to our lambda is equal to 1. So that's interesting. We actually now have two possible basis vectors, and these basis vectors kind of are going to span our eigenspace. So our eigenspace for lambda equals 1 is really the span of both of these vectors. So 1, 0, 0 and 0, 1, 0. So it's a two-dimensional space. So it's kind of like a plane, right? So it almost looks like the xy plane is going to get sent to itself, right? So any vector that lies on the xy plane gets sent to itself.